What might destroy organics on Mars? Well, we don't really know. Brett talked a little bit about, well, maybe the Phoenix detection of organics was hampered by perchlorates. That may be true, but there's also, we know that there's hydrogen peroxide produced in the atmosphere. For example, dust storms or dust devils do some chemistry in the atmosphere that most likely makes hydrogen peroxide. You can imagine that if this kind of sterilizing agent is landing on the surface, that it could destroy surface organics, and that's why we're really going to try and get into the interior of rocks and see if we can find things from very, very ancient Mars. If something sits very near the surface for a while, there's not as much atmosphere on Mars, so these cosmic radiation that helped us detect the hydrogen can penetrate down to the surface, and over billions of years they can destroy organics as well. And there's also natural radioactivity that can destroy organics. So our approach really, we don't know where the organics might have come from. Potentially that might be very, very interesting, signatures of life in the most ideal case. And so our approach really is to look at as broad spectrum of organics as we can and see if we can find. We're on this rover, so we can go tens of kilometers, hopefully, find interesting rocks that the orbital assets point us toward. So we're going to look for this broad spectrum of organics. We have a set of experiments in there also designed to look for things that are really, really interesting from the life point of view, like amino acids and carboxylic acids and amino bases and nucleic bases, which are lots of proteins and cells on Earth. So this is kind of the Pro-E solid model version of what SAM looks like with its 6 GC columns, its TLS, and its mass spectrometer. The fundamental approach is to drop sample in these inlet tubes into a carousel that has 74 cups, so we'll put a sample in a cup. The carousel will then rotate over to an oven. We'll move the cup up into an oven, we'll start heating it up, and we'll look at the gases that come off. The mass spectrometer is similar to things that have been flown to other planets. This spectra actually is from Jupiter. We got in 1995. And this is what the tunable laser spectrometer that I talked about looks like. It bounces light back and forth between mirrors 50 sometimes to increase the path length and get a more sensitive detection for methane. And the chromatography, again, just if we're lucky enough to find a complex mixture of organics, it'll let us separate those out into the individual constituents. Of course, the real instrument assembled in a clean room doesn't look nearly as neat as a Pro-E model, and with all the little valves and heaters and tubes to carry gas around, it's just full of wires running from the control electronics to the various devices. And what we do to test it is we put it in an environment that's almost identical as we can make it to the environment that it's going to sit in the Curiosity rover. So we have a cooling loop that comes from the rover that takes the waste heat from the radioisotope source and then circulates it across the top deck. And so we have a deck that looks just like that in this Mars chamber. We have the distance from the sides of SAM to the walls are all independently temperature controlled. So we believe that the environment in this chamber, full of Mars gases at the right pressure, is almost exactly what the environment is that we'll see on Mars. And so you really need to test these things under conditions that you'll be running them on another planet. The philosophy on that is test as you fly, fly as you test, do everything possible to make sure your experiment sees the right environment. So that's what we've been busy at Goddard working on for the last few years. Is there life in Mars? Was there life on Mars? We still don't know, but one plausible path toward getting at an answer to that question is really doing the best job we can on looking for both heavy and light organics. They certainly may hold clues, and so we're working as hard as we can to answer that question. So launch of MSL in 2011, it'll be an exciting time, stay tuned, and it should operate for 1 Mars year, which is 2 Earth years. That's its nominal mission on the surface of Mars, but as we all know, if you build these things robustly enough, like Spirit and Opportunity, they really may last for a decade or so. So we'll be looking forward to hopefully having everything work and getting data back from Mars in another couple of years. Do we have time for a couple questions?
Questions? Oh, okay. I was curious on the science laboratory, how many of the instruments require an absolute calibration of some measure and other opacities, lengths, that sort of thing? And do you intend to be able to check these calibrations after landing?
Yeah, all the instruments require calibration, and because they're very different types of instruments, they're calibrated differently. Let me talk specifically about how we do it a little bit on MSL. We run gases that we are similar to gases that we expect to see on Mars through our instrument. For example, in the flight instrument, we put a little bit of a sulfate and water containing sulfate and a little bit of a carbonate, and we heat that up. We look for the evolved carbon dioxide and the evolved SO2 and the evolved water, and we get the response of the experiment. What we're doing in our calibration is being very, very careful, however, not to put gases like complex hydrocarbons that might be really interesting in Mars that might stay around the instrument and give us a false positive. So we tend to work in terms of hydrocarbons with fluorinated compounds that have fluorines in several locations. Fluorine is such a low abundance gas in the solar system, or low abundance element, that we're not very likely to see those types of compounds on Mars. So we calibrate out our instrument response with some of those gases. We even bring some of those to Mars so we can calibrate in situ. Another, just to kind of really nail this organic detection thing, which is really important, is we have a standard which is a material that's mostly silica that has some of these trace fluorocarbons that will actually, is on the rover, will drill into. It'll go through the whole sample processing chain, and then we'll analyze the fluorocarbons that are in there. It'll let us know when we're on the surface of Mars whether the instrument is working right and whether the sensitivity that we believe we have is still maintained. But yeah, all the instruments require calibration. We're all writing calibration plans for the Project Science Office and working hard on that.
Would dust be a problem for the spectrophotometer? I mean, you have to have gas sample that gets in there in the path length, right?
Yeah, no, we worry a lot about dust. We not only measure gases coming from evolved solids, but we suck in some of the atmosphere. So we put little dust filters in there.
Okay.
In fact, we've built a dust chamber at Mars where we put some of our components and understand how much dust it takes to really damage them. But we're really trying to keep dust out of our inlet lines with these filters. Just let the gases and the molecules in and keep the dust out. But it really is a worry, yes, for all sorts of systems. We try and design around that. For example, our inlet covers have doors. And so before we're ready to get a solid sample, the door will open, we'll dump the sample in, and we'll close the door. So as we're kind of traversing across the surface, we're not getting dust in the instrument.
Right. Thank you.
Will you be checking for C12 and C13 isotope ratios? Because I've heard that life is depleted in C13 as compared to raw carbon.
Yeah, no, that's really an interesting experiment to make, and we do intend to do that. That's one of the reasons we have this tunable laser spectrometer on board. It measures very precisely the carbon-13 to carbon-12 ratio in CO2 only. It's very narrow bandwidth. And so we'll measure it in the atmosphere. That'll be interesting. We'll look at carbon dioxide that might come from a carbonate from a very ancient rock. That'll be interesting. But then how do we get at carbon in a complex organic that might be in the soil? Well, the way we do that is we bring along a little bit of a combustion gas. We bring along oxygen, and we turn the carbon, the refractory carbon that might be there, into CO2, and then we introduce that into the tunable laser spectrometer. So yeah, that's a really interesting experiment, and we're set up to do that on MSL.
I see, but you won't be looking at the methane this way.
We will also look at the carbon-12 to carbon-13 ratio in the methane. The issue there is that the methane is down at these parts per billion level, and so the TLS can measure methane at even sub-parts per billion. If it really is way down there in abundance, parts per trillion, then the carbon-13 measurements becomes very difficult. But if we're in an area where methane is kind of at these tens of parts per billion, then we should get a good measurement on the carbon-12 to carbon-13 in methane.
I see.